Hello everyone and welcome to our next lesson. In this video, we will be reviewing the core concepts of the second law of thermodynamics, take a look at the entropy balance equation, and define the different efficiencies for thermodynamic systems. This video presents all the concepts and equations needed for the basic entropic analysis of thermodynamic processes. Sample problems will be covered in separate videos. Let's begin with a quote from Vaclav Havel. Just as the constant increase of entropy is the basic law of the universe, so it is the basic law of life to be ever more highly structured and to struggle against entropy. This statement defines an unbreakable universal rule in the second law and then seemingly includes a system that disregards the second law. Biological processes seem to defy entropy as structured compounds and macromolecules are formed from simple molecules. So, how can us living organisms grow into a more organized form when a universal law states that we should be moving towards chaos? The answer lies in our surroundings. The second law of thermodynamics is defined with the following statements. The entropy change of any system and its surroundings, considered together, and resulting from any real process is positive, approaching zero when the process approaches reversibility. Mathematically speaking, we say that the entropy of the universe can only increase. Going back to the case of biological processes, even if the entropy decreases from the organization of molecules, the entropy of our surroundings increases, and the net effect is an increase in total entropy. So even though life struggles against the second law, it, along with everything else in the universe, follows this law. Now we ask, what is entropy? A general description of entropy relates it with chaos or disorder, such that more chaos means a higher value of entropy. Thermodynamically speaking, entropy is generated in every process that shows irreversibility. Also, entropy results from the spontaneous transfer of heat from one body to another. In our entropy balance later, we will view entropy as both arising from heat transfer and on an irreversibility term. Mathematically speaking, we define the change in entropy as the reversible amount of work divided by the temperature. As such, the units of entropy in the SI system is joules per Kelvin. Here is our general entropy balance equation. This signifies the rate of change of entropy inside the control volume plus the net addition or subtraction of entropy from flow streams coming in or out of the system, plus the rate of change of the entropy of the surroundings resulting from heat transfer, and those are equal to the entropy generation term. As a consequence of the second law of thermodynamics, the entropy generation term can only be positive or zero. It is zero if and only if the process is reversible. The third term in the left-hand side of the equation can be expressed in terms of heat transfer between the system and the surroundings through this equation. The rate of change of the entropy of the surroundings is equal to the negative of the summation of all heat transfer terms divided by the temperature of the surrounding. From here on, it is important to remember simplifying assumptions such as when are the terms in an equation equal to zero. For the first term, since this is a time derivative, it has a value of 0 for steady-state processes. For the second term, this is 0 for closed systems wherein there are no mass flow streams. For the third term, which we have represented with this equation below, it is 0 for adiabatic systems because there is no heat transfer in such systems. Therefore, if all of the terms in the left-hand side are 0, we have an adiabatic closed system at steady state. That means that we have an isolated system at equilibrium, therefore there are no mass and energy flows, and the system is at equilibrium. For that system, the rate of entropy generation is zero because entropy is already at its maximum value at steady states in an isolated system. We will explore the mathematical implications of the entropy balance in separate videos when we solve problems. We have previously mentioned that the entropy generation for a reversible process is zero. Here we define the concept of reversibility. A process is deemed reversible when, after taking place, can be done in reverse without any change to the system and surroundings. Reversible processes are ideal processes wherein the total change in entropy is zero and the total entropy generation is zero. The total change in entropy is the sum of the changes in entropy of the system and the surroundings. An example of a reversible process is shown here. We have two springs that alternately push the block. The springs are also alternately compressed and stretched. For this to be a truly reversible process, this must be done in a perfect vacuum so that air cannot contribute to drag. The system must be perfectly frictionless. There must be no influence of gravity. The springs must have perfect elasticity and so many more factors, all of which are impossible to achieve. In the real world, there is no truly reversible process. For example, let's say that you are studying and you dropped your cup of coffee and it shatters on the floor. The only way that this process becomes reversible is if you borrow the time stone from Doctor Strange and you reverse the arrow of time. If time is reversed, your coffee cup will spontaneously assemble itself, gather the spilled coffee, and float back up to your study table as if nothing has happened. Since we cannot time travel yet, such reversible processes are impossible. Moving on, let's describe the concept of ideal work. Under the assumption of complete reversibility, the ideal work is the minimum work consumed for processes that require an input of work or the maximum work produced for processes that generate work. Here is the derived expression for ideal work. For open systems, it is equal to the net rate of enthalpy addition or subtraction coming from the flow streams minus the surrounding temperature multiplied by the net rate of entropy addition or subtraction from the flow streams. This does look like the equation for the determination of Gibbs free energy of a system. After all, the change in Gibbs free energy is the maximum amount of useful work that can be extracted from a process, much like the ideal work. Given the definition of ideal work, we can now define the amount of lost work. Lost work is the work that is wasted by the irreversibility of the process. This is simply the difference between the actual work and the ideal work. For reversible systems, there is no lost work. Lost work is also called irreversibility, and it can be determined from the product of the surrounding temperature and the rate of the entropy generation. Our definition of a completely reversible process involves a lot of zeros. That is, zero total entropy change, zero rate of entropy generation, zero lost work, and zero irreversibility. This simplifying capability is useful in some calculations, but the results may not be very accurate because, again, there are no real reversible systems. For the last part of our lecture, we will talk about the different representations of efficiencies. First, we have thermodynamic efficiency. This represents the degree of extraction or utilization of work and is based on our previously presented definition of ideal work. For systems that require or use work, the thermodynamic efficiency is ideal work over actual work. For systems that produce work, it's the reciprocal. It's actual work over ideal work. Basically, the larger quantity is always at the denominator. This measure of efficiency is based on the reversibility of the system, such that a higher thermodynamic efficiency means that a process is nearing reversibility. The second type, thermal efficiency, is broadly defined for most thermodynamic devices as the ratio of the output to input energies. It can also be viewed as the ratio of benefit to cost in terms of energy. We will go back to this concept in our future lessons, but for now, here are the definitions of thermal efficiency for different devices. For heat engines, it is the ratio of work extracted to the heat supplied. For refrigerators, it is the ratio of heat removed to the work supplied. For heating devices, it is the ratio of heat output to heat input. Thermal efficiencies can also be defined for thermodynamic cycles, which we will discuss in future lessons. Finally, we have the isentropic efficiency. This concept is very similar to the thermodynamic efficiency. It is defined for the thermodynamic processes as the ratio of the actual work required or generated to the isentropic work. At first glance, this looks similar to the thermodynamic efficiency. We just replaced the ideal work with isentropic work. The key difference here lies between reversible and isentropic. Isentropic processes are both reversible and adiabatic, therefore ensuring that the entropy remains constant. We will go back to this concept when we discuss flow devices. With that, we are at the end of this lesson. Here are some important takeaways that we must always remember and apply in our future lessons. The total entropy always increases or stays the same. There are no truly reversible processes. Losses in work arise because of irreversibility. A completely reversible process implies zero entropy generation. And an isentropic process implies no change in entropy. That is all for this lesson. I hope you've learned something. Thank you for listening, and as always, keep safe.